Get your eye clickers ready. We're going to do a clicker question. Shh, 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 shh. We're going to do some clickers in a second. I'm going to go over some grading procedures and stuff. First of all, in the Great River Learning website, the chapter mini reviews, we got a bunch of them. One of them already on the books, that's chapter 2. I was trying to upload those into web courses, but there's a few of you that didn't put your NID in. You put in your PID. All right, now the NID is 2 letters and then a bunch of numerals. The PID is a bunch of numerals. All right, that's the number on your ID card. We don't want that in Great River. We want NID. Now, some of you I've already alerted to that, the rest, I still have about a dozen of yous in this section, and I got all the first section, the 9 o'clock section to do. So I will alert you if you're one of the people. And I know that Justin over here and Monica over here have already figured out how to change PID over to NID. If you don't have anything in there, I don't know, I suppose that'll work too, if you don't have anything. Some of you didn't type in anything for your NID, so you guys are on my bad list because you're holding up the upload process. So go ahead and get that squared away ASAP, and I'll probably be sending out some more messages this afternoon. A bunch of you have already gotten messages, and so what I think, and what I've been telling people that have messaged me back is go into Justin's thread in discussions how to get the NID in Great River account, and his method and then Monica's method will work. And you guys, I checked yours this morning, your NIDs are in, so it's all looking like a righteous method. So go ahead and do that if you haven't already. We'll get that squared away. And then as soon as we get that all squared away, then I'll upload your Chapter 2 mini review. By the way, the mini review in Great River is a whole number. It's not a whole number. It's a number between 0 and 100. And that's to represent a percentage. Now, I never put points in web courses like that. So I'm going to convert that into some fraction of 14. So you're going to have, when you see it in web courses for Chapter 2 mini review, it's going to be a number between 0 and 14. And it's just going to be basically that number that you have in Great River divided by 100 and multiplied by 14 and then rounded off to the nearest whole number. So that's what you'll see. And we're at the point now where you can start tackling the Chapter 3 mini review, which is actually been available to you since the 20th. So that's a week ago. All right. I think I activated it to start after exam 1 was on the book. So that's a week ago. Anyways, we're going to have a Chapter 4 mini review. We'll probably be done with Chapter 4, which we're going to be talking about today some more. We'll be done with Chapter 4 next week, so I'll activate that one. And we're going to have more homework over there in Great Rivers, and the great bulk of you are registered for that, so that's good. Although not everybody did their homework. A lot of you guys didn't do anything with the Chapter 2 mini review, so you want to start doing that. with chapter 3 and chapter 4 and so on. Just to reinforce, we're going to have significant amount of homework in Great River with the textbook, and we're also going to have a significant amount in web courses. So be alert to both of those. Now, I'll try to let you know ahead of time about Great River because that's much harder to set the date. So, the ones in web courses, I can reset the date till it takes about 2 seconds. Great River, it's a little tougher. So I'll be announcing it in class, but sometimes web courses I might change the due date, an extra day or something like that. I can do that in a snap. So, but anyways, it'll be announced and so forth, and that'll be good. So just stay alert for that. Questions? Okay, let's keep going. I want to do a grading example with you. We're going to take iClicker data, and this is from a real student. I'm not going to say who it is. Oh, no, I made this one up. This is John Q. Student. What we're going to do is take some imaginary clicker data and convert it into participation points. Now remember, that's 25 points out of 250, so 10% of your grade. It's a little bit tricky if you haven't participated at the level of 85% or more. All right, so let's take a look at the data. So, this is the John Q. Student example. As of Tuesday, lecture 11, we had 20 iClicker questions on the books. So that's lecture 6 through lecture 11, but not lecture 9 because that was the exam. That's separate. Those we had clicking, but that's in your exam grade. Okay. So regular lecture from L6, L7, L6, L8, because I think we skipped one lecture. L9, L10, and L11. And so a total of 20 iClicker items. So now let's say that, for instance, John Q. Student has answered 13 of them. Okay, so go ahead and write that down. John Q. Student, 13 answers out of 20. So just divide 13 divided by 20, and that's 65%. All right, so that's his participation rate. Now, when I post your data for participation, which I hope to do this weekend, your first roundup, and it'll probably include today's data, so several more than 20. So we might be up at 24, 25 after today. But at any rate, you'll see how many you answered. You'll also see how many you got correct. So you just divide by how many possible, and as of Tuesday, it's 20. So if you have 85% or more, you're done. You don't have to calculate, that's the level that triggers full participation pointage, 25 out of 25. So but this guy doesn't. John Q. Student, he's below that. Right? So what we're doing is and most of you guys are going to be above 85% without breaking a sweat. There's going to be a lot, that's right. Somebody up here in the front just went, whew. There's going to be a lot of 25s out of 25s, and the people that don't get 25 out of 25, a lot of them are going to have 24 out of 25. All right? And this is how you calculate the grades if you're below 85%. It's a little trickier. Homework, you just figure out your homework percentage and then multiply by 25, and that's your homework points. Okay? But for clicking, it's a little bit trickier. Now, let's say also that John Q. Student got 11 of them correct. So he's doing good on the questions that he's answering. 11 out of 13, that's not bad. But 13 out of 20, so he's missed a couple lectures. All right, so he's a little shaky. He's below 85%. And if you guys miss more than 1 or 2 lectures this semester, unless it's, like Tuesday lecture, we only had 1 question. So if you miss Tuesday, and then you probably have another 2 lectures to burn. But for most people, it's 1 or 2 lectures. And if you miss 1 or 2 lectures, you're still going to be above 85%. All right, but if you miss more than 1 or 2 lectures, you might start dipping down into this guy's territory. And if it happens to you, it's not permanent because we're going to be asking questions until December. So you can build it up. You miss 1 too many lectures, you can build it back up because we got more questions coming. Anyway, so he's got 11 correct. Now, the thing I want to mention to you is that why do I keep track of how many you get correct? The reason I do that is I want to see how well you do. I mean, because the questions, I usually have a correct answer or I award correct. If it's a survey type question, I give everybody a correct answer. But if it's a calculation or something, there's going to be a correct answer. All right, so I always want to know, and I'll always grade it correct or incorrect. At the end of the semester, if you have more than 75% correct, you get 4 bonus points in your semester grade. And that's almost 2%. So 4 divided by 250 is 1.7, no. What is that? 4 divided by 250. 1 point something something. What is it? Yeah, 4 divided by 250. 0.016, 6666, right? No? Just 0.016. So it's 1.6%. All right, so that's a nice chunk of change. All right, so I keep track of both how many you answer and how many you answer correctly. All right, now the participation is from how many you answer. So that comes out of the 65%. But don't forget about the correctness. All right, you want to get that as high as you can. So basically, you get those 4 bonus points if you get a B on your iClicker questions. 75%, that's a B. I mean, if I have 100 iClicker questions by the end of the semester and you answer 75 of them correct, that's 4 bonus points. And you can just think about tacking them onto your final exam grade, final exam score. So, anyways, let's get down to business. Now, I want to tell you how I style the clicking data. I keep track of 2 numbers. This guy, John Q. Student, in the grade book, there will be a line. It'll say, clicking roundup as of, what's today, the 28th? What is it, 28th? 27th. Okay, so clicking roundup as of 09/27, all right? And that'll be, and I'll give you a number, and it'll be 2 digits and then a decimal point and then 2 decimals, 2 decimal digits. So it'll be something point something something, all right? This guy would have 11.13. The whole number part encodes his answers that are correct. The decimal part encodes how many he answered. All right, so he answered 13, so his roundup number is something point 13. 11 of them were correct, so his roundup number is 11.13. All right? Now the problem with that is, just so you know, web courses, I'll answer, if you have like 20 or 10 answers, if you've answered everything, 20 questions, your decimal part will be 0.20. The problem with that is web courses, Canvas, will just display that as something 0.2. It won't be 0.20. They add those extra zeros on questions, and they strip the zeros out of the trailing zeros out of the grade book. I don't know. I can't get them to do it right. But anyways, that's what you're going to have. So when I put those in this weekend, everybody's going to have something, point something, something, and that encodes how many you answered and how many you answered correctly, right? Now the pointage out of 25 comes from the correct, from the answers. So that comes out of the 65%. So he's going to have to, John Q. student is going to have to solve this proportion. Here it is. All right? You take his percentage and divide by 85%. And that's on the left-hand side of this proportion. And then the right-hand side, his pointage, so that'll be some number between 0 and 25. And then down in the bottom on the right side, in the denominator, 25. And that is how we encode the arrangement of points that John Q. student is going to get. All right? Now, we got to solve that. Make sure you jot, and here's was 0.65 in there. Now, I'm going to ask you a clicker question here in just a second. So have your clickers out. Matter of fact, let me just set it up here. And it's going to be numeric. And I'm going to ask you, how many points does John Q. student have? So you're going to figure out the numerator on the right-hand side of this proportion. So jot it down in your notes, and then you're going to have to do cross multiplication and stuff. Okay, and figure out what it is. All right, so take a second to jot down that second equation block. Now, when you get your roundup numbers this weekend, you might have, 0.71 for 71%. And if you have 0.86 for 86%, ding, you're done. You don't have to do anything because that's above 85%. So anytime you come in at 0.85 or higher, just write down 25 points out of 25 for me. This is only if you're below 85%. All right? The haircut's looking fine. Good. I got to get mine done. I'll show you in here in just a second. Okay? Because it's in the syllabus, actually. All right, so here we go with our clicker question. Everybody's here now. All right. All right, John Q. So here's the same data. John Q. student. And on this one, you were asking me, what do we round up to? Always go up. So if you have 12.00007, it's not a math problem, it's a grading problem. So in the math department, 12.0007 would round off to 12. But in this class, 12.0007, 13. So that's my way of giving you the benefit of a point, benefit of a round up. So go ahead and type in your, wow, you guys are fast. Let me see if you guys are getting it right. Oh my goodness. Oh my gracious. You guys are, we got some splaining to do here. Whoa. I can't give away the question. I can't, you're going to have to, 30 seconds. If I tell you, I can see people with the wrong answer, but I can't tell you what to do to correct it without giving away the answer. So you're just going to have to suffer, I guess. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You guys are doing good. All right. So 60. Raise your hand if you got 20. Nice. That's the correct answer. Okay, so John Q. Student gets 20 out of 25. All right. So, and you guys that typed in 19, you did a math department round off, not a Dr. B participation points round off. I always round up, no matter what the decimal fraction is. Okay. And this one I definitely chose 13 out of 20 because I knew it would be 19 point something that tempts you to round down to 19. It looks like I caught a few of you napping on that. Keep your clickers out. We're going to do some more clicking. But let me just point out to you that we are going to be, every time I publish your clicking roundup, and I'll do it 3 or 4 times this semester, you'll be able to recalculate your clicking percentage in this way. First, start with your percentage. Your participation percentage. How many did you answer out of how many? 13 out of 20 or whatever it happens to be. If that number's above 85%, ding, 25 points. You're done. If it's below 85%, do this. All right? So you can always figure out kind of where your grade is at. Okay? And your homework, just whatever your homework percentage is, multiply that by 25 and round up. That's easy. You don't have to do a proportion, it's just straight percentage. And then your exam, so right now we have 100, right now, as soon as I publish your clicking data, something, point something, something, you'll be able to do this. And then you could do your homework, that's pretty easy. And that's so something out of 25 this way for clicking, something out of 25 for homework, and then something out of 50 for exam 1, so it's 100 official points. Okay, and you can figure out your percentage, and then go look at the syllabus and look on the percentage column, and you'll see what grade you have. Okay, so 50% or higher is a D, 60% or higher is a C, 75% or higher is a B, 90% or higher is an A. All right, that's what's on the syllabus. So you can always figure that out. Also, the other thing is, if you have we've got a couple bonus points on the books for many of you. So what you would do with that, add that to the numerator, but don't add it to the denominator. All right. So the official denominator is regular points, how many possible. And the numerator of your grade is how many regular points you've got plus how many bonus points you've got. All right. So just add those straight into the numerator. Don't touch the denominator. All right. Now, before we go and talk about recoil, I'd like to stop for questions about this process. Okay. Let's talk about the recoil problem in the homework. I had a couple students in both sections ask about it. The key concept is this: whatever the bullet gets, the rifle gets the same amount but in the opposite direction. So here's kind of a little schematic drawing of a bullet in a gun. All right, that round black sphere is the bullet. And that little gray rectangle behind it is a little bit of gunpowder. And then the black rectangle that's open at one end, that's the gun barrel. Right? So the bullet's going to go off to the left. And in the problem in the book, I think it was number 2, not in the book, but in the homework, it was number 2, I believe. I gave you a velocity and a mass, 0.025 kilograms for the mass, and then some number, it varied each time you took it, 230 or whatever it happened to be, meters per second for the bullet. Okay, and that's the velocity at the other end of the gun. So here's my animation for the day. All right, the the gunpowder is going to blaze. Nice. Pow. Okay, it's pretty hot, huh? So at this point out here, the bullet's got its final momentum, its final velocity. Right? And that's, whatever it was in the problem, 234 meters per second or whatever it happens to be. And the mass you have, 0.025 kilograms. So just multiply those together. Now that's off to the left, so it'd be a negative something kilogram meters per second. The rifle is going to recoil. Now watch this recoil. This is thrilling too. Here it comes. The rifle's going to recoil. Yay. The rifle doesn't recoil very much because it's so much more massive than the bullet. Unless raise your hand if you ever go hunting for deer and stuff like that. A couple of you. If you ever go hunting with a rifle, high-powered rifle, you'll get a significant kick. You'll feel it. But, so it depends on what kind of ammo you're using. But the other thing I want to point out to you is that all this occurs in a set distance. Now, for a rifle or a artillery piece, any kind of a gun barrel, the interaction distance from initial to the end of the barrel is just the length of the gun barrel. Okay, so that's fairly easy to calculate. And what we're going to do for homework this weekend, I'm going to give you a brain burner in which you have to calculate not an interaction distance, but a stopping distance, which is kind of the reverse of this. But it'll be related to impulse and stuff, and I'll kind of give you an outline at the end of class for that. But before we go to that, I'd like to talk about collisions. Now, I want you to take careful notes. And we're going to talk about some box cars. And, out west, where I used to live in Montana, the trains, you see the freight trains going, through. I mean, they follow the river. The interstate follows the river. Trains follow the river. And people live along the river. The Yellowstone River, the Missouri River, mostly. And so trains, you can see, it's easy to see them. And one thing about trains, they build them up in the freight yard. They build a big long string of 100 cars or more, box cars and flat cars and stuff, and they just bump them into each other, and they'll automatically latch on. So that's what we're going to study. And the nice thing about this interaction example that we're going to do, this example, the box cars, and then the example of the skateboarders, really is effective for understanding an enormous amount of physics. Because the coin of the realm is momentum. Sir Isaac Newton, F equals ma, he was thinking in terms of momentum. Now, at the end of class, we're going to talk about Einstein and what his addition to the theory is. It's pretty interesting. But for us, momentum. So let's talk about this example here. Now take careful notes, and we'll go through it nice and easy, step by step. And our situation is this. We're going to have a string of 3 box cars over here on the right at rest. And a 4th box, it's actually box car number 1 in my notation, coming in from the left, and it's going to have a speed of 4.4 meters per second. Now what's going to happen is they're going to interact. They're going to bump into each other, like bumper cars at the fair. Or that... They don't have bumper cars at Disney World. What is that ride where you get in and the teacups? Isn't that? I hate that, because I always get a really bad headache from that. Because you go so fast. If you don't do it right, you're going so fast. Oh my goodness. But anyway, so bumper cars here. So, and the thing about box cars, they're going to latch together. Right? So the number one is going to bump into the string of three, and then they're all going to move off to the right at some other new velocity, v subscript new. And that's what we're going to try to figure out. Now, all the box cars are identical. So we're kind of idealizing it a little bit, and we're ignoring friction and air resistance. We're just saying that there's no unbalanced external forces. The only forces that are acting in this evolution are the interaction forces of bumping into each other. All right, right where that yellow panel indicates. All right, and that's, when they bump into each other, you'll hear it. You'll hear a little bit of a boom, and then they'll start moving off to the right as one big unit. All right? So let's take a look at trying to make sense of all this. So the mass of each one is 35,000 kilograms. All right? This one, number one, is moving to the right. So go ahead and write in a velocity arrow for it, V1. All right. And these other guys over here, these are boxcars 2, 3, and 4. Those are at goose eggs, 0.0. They're at rest, 0.0 meters per second. So the momentum for those guys is also 0. Now what we're going to do here, there's no unbalanced external forces. There is third law interaction force when they collide in this collision. All right? And so whatever delta P the three boxcars get, number one boxcar is going to get the same amount of delta P, but in the opposite direction. Now let me ask you a question. I want you to think. Boxcar number one is going to get some delta P. He's going to have a force acting over time. He's going to get some impulse. Okay, so boxcar number one, going to get some impulse. Is it leftward impulse or rightward impulse? Raise your hand if you have an idea. What do you think? Leftward or... I see some guys going like this, and I see some guys going like this. So what do you think? Here's another one going like this. Raise your hand if you want to answer. If you want to stab at a crazy, wild and crazy answer. Nobody's... Okay, red shirt man. Leftward? So you're saying that boxcar number one is going to get some leftward delta P? Well, that would mean that it's going to get a leftward push force from the three boxcars. Is that what you're trying to say? Well, if the third law is correct, then that means that the three boxcars are going to get some rightward push force from number one. So that means right? Okay, good. So what's your name again? Yeah. Leonardo. Leonardo just went like this when I said that. So the third law says push force to the right for the group of three. So delta P to the right. They're going to go from 0 to something. Kilogram meters per second. V1 is going to get a push to the left. So some leftward delta P. So whatever momentum he has coming in, he's going to have less after the interaction. And here's the kicker. They're all going to be going at the same speed because they're all hooked together afterwards. Now we're going to use that to figure out that new speed. Here we go. First of all, calculate the total momentum of all four boxcars and add them together. All right? Because there's no external forces acting, we're not going to, What boxcar number 1 loses, boxcar 2, 3, and 4 together are going to acquire. So there's no momentum that goes missing. But the total is boxcar number 1, so 35,000, that's M. V is 4.4 meters per second. All right. Now, the other 3, I put them in, you don't really have to, but I put in 3 goose eggs, 3 zeros, because they're at rest. Right? Now, they're not going to be at rest after the interaction, but initially, yes. All right. So the total here, anybody verify me 154,000? Get your calculators out, start verifying. And you're going to have to do some calculations here in a minute. Got it? Okay, good. All right. Now, there's no, they're exchanging momentum, but the total is not going to change. So the momentum afterwards, P subscript F, P subscript final, is also going to be 154,000. Now, I'm going to ask you a question on your I clicker. So go ahead and write down PF equals PI. All right, whatever it happens to be, 154,000 kilogram meters per second. And, in reality, boxcars are not going to be exactly the same size, but we're doing this kind of just for a workout, just for conversational purposes. Well, you can measure, and, it might be a little trickier if they're all 4 different, but we can work with it. So I'm going to ask you a question. Hit the refresh key and answer this question. Riddle me this. Why must the initial momentum state of the boxcars, P subscript I, equal the final momentum state of the boxcars, P subscript F? So think about that. How would you answer that? So type in a letter and hit the send key. And you can use your buttons A, B, C, D, or E if you want, but you still have to hit the send key. And go ahead and write down the question and write down your answer as well. This is actually by way of being notes. A question and an answer. 20 seconds. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Somebody typed in 2 letters. The correct answer is momentum is always conserved, and why is it conserved? Because they exchange equal but opposite momenta. When you're talking about interactions, equal but opposite reactions, like Newton's third law, that's the famous phraseology of it. What you really want to think of, equal but opposite, are equal but opposite momenta exchanged. So whatever rightward momentum that boxcar 1 loses at the bump, the other 3 acquire. And boxcar number 1 gets the same amount to the left. Right, so he slows down with some leftward delta P. So let's continue with the problem here. All right, so PI and PF are both 154,000 kilogram meters per second. Nice. All right, now, go ahead and make a note that those two numbers are the same because of this. The concept that we use for that momentum is the same before and after, is conservation of momentum. In other words, the momentum doesn't disappear. It can be rearranged, like in your dorm room. You rearrange the furniture in your apartment or your dorm room, but that it doesn't suddenly disappear unless some maniac comes in and steals when you're not looking. But other than that, nothing disappears. All right, now, the other thing, how is this going to help us figure out V new? The new speed of the block of 4 boxcars moving off to the right. How's that going to help us? Well, V new, you could call that VF if you want, V final, of the entire string of 4 boxcars. And that's, if you just plug in the definition of momentum, P equals mv, yeah, you could do that. Put in an equal sign and then mv, and that's the mass of the string of 4 boxcars. And just think to yourself, you got 4 of them, and they're 35,000 kilograms each. They're pretty big, 35 metric tons each. All right, and you got 4 of them. So what's 4 times 35? Calculate it out in your calculator, and you'll see that it's 140,000. All right? So that's the mass. So this thing is like one big mass, because they're all connected, fairly rigid connection. And they're moving at a certain speed off to the right. And V subscript new, the new speed to the right, that's what we're going to figure out. You can look at it. Can you see it there? It's the only unknown now in this equation. So we've used conservation of momentum to get the left side and definition of momentum to get the right side. And now we're solving for V subscript new. So we're able to do that. All right, so let me park this up here. All right, so there's our combo equation. Conservation of momentum gives me the left side, Laura, and definition of momentum gives me the right side. Do you have a question? Okay. So now we're ready to solve for V subscript new. How do you do that? Oh, you just divide both sides by 140,000 kilograms, that's all. And you know what? If you look at that, kilograms cancels from the bottom and from the top. But meters per second on top, no cancellation. But that's all right, because we have to try to keep meters per second, because what we're trying to figure out is a speed. So we're doing good. Now we just got to calculate. Anybody have a verification? 1.1. Anybody else verify that? 1.1? Okay. All right, you got it? Yeah, okay. All right. Now, I'm going to give you a calculation question. And have you jotted down everything? 35,000, 4 of them. Because I'm going to calculate now with you, or I'm going to ask you to calculate with a new interaction time. So hit the refresh key. And here's your problem. Different V1, 6.4 instead of 4.4. But everything else is the same. All right, so take a few minutes to calculate this. Consult with your neighbor. Discuss if you're sitting next to somebody. If nobody's sitting next to you, it's always good to make friends in class. and sit next, except if you talk a lot. But but it's all right to talk now when you guys are calculating. That's all right. You're up close so I can go shh easily. Not you, the girl behind you. I know you can hear him, right? Yeah. That's all right. That's one of the fun things about teaching. All right, what's the answer here? Oh my goodness. Hey, are you going to have a number, just curious, bigger than 1.1 or less than 1.1? I mean, should be bigger because your input velocity is bigger. So you're going to get something above 1.1 probably. If you get something less than that, you may have blooped something up. So that's my tip. And I can see I can see what you guys are typing in here, so this is good. Make sure you have the decimal point correct. I can't tell you without giving away the answer, but $45 seconds. $30 seconds. $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, 86% of you got it correct. Raise your hand if you voted for 1.6. Sweet. Yeah, so that's the answer. Now, if you have another problem on the homework this weekend, I'm going to give you a collision of two objects that are coming at each other. Now, when you see that, I want you to do total momentum beforehand, but one of them is going to have positive rightward momentum, and the other one's going to have negative leftward momentum. So make sure you're ready to handle that. And then afterwards, they're going to hook together like, it's going to be like two boxcars. And they're going to go off, and you're going to have to determine, is it leftward or is it rightward, based on the numbers that you have. All right? And it's going to change each time you do the attempt. All right? It's going to be, so just be ready to handle direction, but basically the same thing. Instead of having a bunch of zeros, you're going to have a negative over there in the initial momentum, P subscript I. And you're only going to have two objects. But for one of the, I think I'll probably give you a boxcar problem too. And then that'll be a little bit more like this one. And then I'll give you this special one of two objects colliding. And it's this whole idea of conservation of momentum is phenomenal. The just as free fall was this huge, lovely, serendipitous decision by Galileo to study the most simple and most handy acceleration there is. Also, the skateboarder example up here in the front and boxcars, colliding together, those are two very simple examples that help you understand almost every interaction in physics. The only exception is stuff like some things in optics, which you have to understand waves in order to figure that stuff out. But other than that, those examples, that's it. You can usually, the fanciest physics interaction, like galaxies. Our galaxy, the Milky Way galaxy, is interacting with the nearest spiral galaxy, which is called the Andromeda galaxy. It's actually a little bit bigger than our galaxy. And they're orbiting, just like planets orbiting, or like binary stars, except these are big, huge not blobs, spirals of stars. And all those stars in the Andromeda galaxy, they're interacting with each other. They form a spiral. And the same thing in our galaxy, the Milky Way. And then, you know what else we got? We got Andromeda over here. You can see it in the summer in the constellation Andromeda. And we got the Milky Way galaxy, that's our galaxy. And we got a bunch of little dwarf galaxies like the Large Magellanic Cloud that you can see in the southern hemisphere pretty easily, and the Small Magellanic Cloud. And we can see individual stars in those if they're bright enough and if the seeing is good. But they're all interacting gravitationally, and boxcars and skateboarders help us understand that, as fancy as those are. Nuclei, the interactions of neutrons and protons inside the nucleus, the smallest unit that we know in nature. Boxcars and skateboarders will help out quite nicely in that. So from nuclei to galaxies and beyond and everywhere in between, yeah. Here's the, so that's this point here, skateboarders, and you should put in skateboarders and boxcars. The total, here's an English sentence to encode this idea of conservation of momentum. Because momentum is the coin of the realm, the coin of Sir Isaac Newton's realm. When we put Sir Isaac Newton in the driver's seat, this is how he's thinking in terms of momentum. And the total momentum of a group of interacting objects, skateboarders, boxcars, galaxies, protons and neutrons in the nucleus, they'll remain the same in the absence of external forces. Now, in the nucleus, there's a strong nuclear force holding it all together. Galaxies, gravitational force. Electrons and nuclei, electromagnetic. That's the electron is bound to the positive nucleus by electromagnetism. So that's the third force. But externally forces, so in an atom we don't really worry about gravity too much. But in galaxies, yeah, that's the only thing we really worry about a whole lot. So it's kind of cool. Now, so that's an English way of expressing this idea. And you'll see other versions of it stated. And I think I have a slightly different version in the textbook. But yeah, galaxies to nuclei and everywhere in between. But as we're going to find out in just a few minutes, Albert Einstein said, you know what? Isaac Newton, momentum, the quantity of motion. Yep, that's the coin of the realm. But I have an addition. And his addition in four-dimensional space-time is what we're going to study in just a second. But before we do that, I want to give you a sneak preview of a homework problem. Now, I don't know if I'm going to give you this one, but it's going to be like this one. And so take notes. You observe and video a little shrimpy kid taking a spill and slide to a stop at the skating rink. And you know, raise your hand if you've ever been ice skating. It's nice. I love ice skating. I love skiing. I love ice skating. You know what? I've never been to a roller rink. Raise your hand if you've ever been to a roller skating rink. Dang, I got to go. Maybe that should be my homework assignment. I've done a lot of things in life, but I've never done that. Anyways, so all right, so the little kids, so this problem, the little kid's mass I'm going to give you, 30 kilograms in this example. And I'm going to give you his initial speed. Now he's going to come to a stop, so so initial speed 3.4 meters per second. Good. So you can figure out his momentum, his initial momentum, P subscript I. All right, that's good. His final momentum, what's his final momentum? 0, that's right, because he comes to a stop. So you can figure out delta P. And what formula is delta P a big part of? Impulse formula. All right, so now, but we have to have a force for that, and we got that. Because your uncle owns the running rink, runs the skating rink, and so you know that the friction force F on the little kid is 19.2 newtons. All right, now in real life, nobody goes around measuring friction forces on little kids at ice rinks, but let's pretend that your uncle did, and so he knows at 19.2 newtons, all right? So you've got enough information to figure out stopping time using the impulse formula. You could do it. We've done it about 7 million times already. But now what if I ask you what the stopping distance is? And that's what this problem is about. It's kind of small lettering, but right down here it says calculate the stopping distance to the nearest 0.1 meters. All right, let's take a sneak preview of that. All right? Because, and here's the secret weapon. And I want you to think about this weekend. In addition to using impulse formula, you can also use a velocity graph. Now, in this problem, it's a velocity triangle. He starts out 3.4 meters per second up here, and he comes to a stop down over here. Now, what you've got to figure out, and it'll be a different stopping time each time, but you can figure it out, delta T. Use the impulse formula. No great shakes about that. We can do it. So in this case, let's do it. Let's go ahead and make notes. The little shrimpy kid, friction force, 19.2 newtons. And delta T we want to figure out. Now, we want to figure out delta X, his interaction distance, his stopping distance. But before we can get to that, we got to get delta T. And why is that? Because if I can get delta T, I'll have a velocity triangle, completely specified. And then I can get a distance from that. Okay, so here's my MV. And so, I'm kind of skipping a step here because this final is 0, so I'm just not even writing down that. So this is his This is pi, 30 kilograms times 3.4. Okay, go ahead and verify me on that. 102 kilogram meters per second. Whoa, that's the letter 2 in there. That's supposed to be an S. That's supposed to be kilogram. I must not have been wearing my specs when I typed that one in. Okay, so 102 kilogram meter per second. So solve for delta T, as we've done before. Anybody got an answer on that one? 5.3. Anybody verify over here? Okay, good. 5.3125. Good, that's what I've got. And then, okay, now you can write that down over here for your velocity triangle. And now you have base times height times 1/2. Triangle is 1/2 base times height. So the base is 5.32125, and the height is 3.4. So 1/2 base times height. All right, so here's base times height. Just multiply those two babies together. And anybody verify me on 18.0625? Okay, good. Anybody over here? Good, okay. Always bring your calculator and verify me. Do not let me catch you napping. Because every once in a while, even you guys in the back, I'm going to see if I can catch you guys napping. Nope. It's impossible, right? Okay, good. I like that. Good. Somebody in the back is going, no, Dr. B, no. You won't catch me napping. So this is the distance, right? That's pretty much it then, right? No? I heard somebody say no. Yeah, you got to divide by 2. So divide that by 2, and we want to the nearest tenth. So 9 point something, and in this case it'll be 9.0. So there's my answer, stopping time. So if you get this problem and you want that 2 out of 2, you just burn it in there, 9.0. Or whatever the numbers tell you. Let the numbers do the talking. All right, now we got a few more minutes. Let's talk about Sir Albert Einstein, the master of all 4 dimensions. And here's the question. We've been talking about, Newton's third law, impulse, collisions, interactions, skateboarders. How does that all work out in 4 dimensions? Time being the 4th dimension. So here's a little recap. The 4-dimensional view of the universe, spatial dimensions, there's 3 of them. And in relativity, you have to distinguish them. So X, Y, and Z. And then the 4th dimension is temporal or time, usually symbolized T. And so if you want to remind yourself the arrangement of the spatial dimensions. So if you think of the stage here, and if the y-axis goes left and right, and the x-axis goes toward or away from you guys, and the z-axis goes up towards the sky, that's one way to set up the 3 spatial dimensions. There's other ways to do it. Latitude and longitude and distance from the center of the earth. That's spherical coordinates. But for rectangular coordinates, x, y, and z, that's perfectly fine. Now, dynamical quantities. X, y, z, and time, those are the 4 dimensions of space-time. That's actually geometric. It's a position. But what about forces? What about momentum? How do you do that? Well, the thing that you do with momentum, it's a mass times a spatial velocity. The velocity has an x, a y, and a z component. All right? And P equals mv. Please stop talking over here on the right. Whoever's talking over me. All right, so now The fourth component, momentum, px, py, pz, that's good. Spatial. The part that kind of corresponds to the temporal part of dynamics is energy. And you've all seen this famous formula, equals mc squared. Yeah, that's energy. That's what we call the rest energy. And Einstein came up with that concept 113 years ago, approximately, 1905. The energy that an object has just because it exists with mass. Now, photons, particles of light, they do not have mass. They still have energy. But anything that does have a mass, this is the energy before they even start moving, before they're in an electric field, before they're in a gravitational field. Just because they exist, they have this, and it's an enormous amount of energy. By the way, in a nuclear reaction, changes in this, mc squared, a little change in the mass of the nuclei after the nuclear reaction, that change in the mass goes into energy. And that's the energy that powers the sun. And it's called fusion, nuclear fusion. And a little bit of mass gives an awful big amount of energy. You've heard on this TV show Star Trek, in the movies, Star Trek movies, the matter and antimatter engines, the dilithium crystals. There is such a thing as dilithium, and I suppose there's dilithium crystals, and there is such a thing as matter and antimatter. And when they come into contact, they annihilate and become pure energy. It's not missing mass, it's complete. All the mass, the rest energy is converted into pure energy, photons of light. So that's from this equation. Huge equation. So again, here are the three spatial dimensions. Here's the spatial momentum, MV, MVX, MVY, MVZ. And then there's the picture of the three spatial dimensions, X, Y, and Z. And in terms of vectors, here's a way that you could express. Now this is the spatial part here, this diagram here. All right, so spatial. But in 4 dimensions, we got to add one more component. And here's how we do it. Space-time position, time, X, Y, Z. And usually we would put time in the very first slot, and then the 3 spatial dimensions after that. Sometimes you see it the other way around, and then dynamically, if you're trying to be like Sir Isaac Newton and think in terms of forces, interactions, third law, skateboarders pushing off from each other, a bullet out of a gun, the recoil. You got to think about momentum and stuff. But I keep saying that. Albert Einstein said you have to have energy in the equation as well. And that goes in the top slot. And so this is, instead of having a vector with in parentheses, X, Y, and Z in parentheses, this one's stacked as a column. But it's the same thing. So energy. So as I said, Sir Isaac Newton, when he wrote his famous book, the mathematical principles of natural philosophy, the very first page, he was talking about momentum, the quantity of motion. For him, that was the coin of the realm. All the interactions of nature, he used and interpreted and modeled and studied in terms of quantity of motion, the momentum. And Einstein said energy is just part of a bigger 4-dimensional vector. So this is actually called, in some relativity physicists, such as me, we call this the 4 momentum. In other words, it's momentum with a 4th slot, and the 4th slot being occupied with the energy. So all your kinetic energy of motion, all your gravitational energy, your pressure and density, the pressure of a gas encodes energy. It goes in that top slot. And that is the coin of our four-dimensional universe, the coin of the realm. Now, Tuesday we're going to study energy. So read all the way through chapter 4. There'll be some homework for you tomorrow by lunchtime. And let's dismiss a few minutes early. See you on Tuesday.